Hey everyone. So I know this is coming out a little late, but we are going to work through worksheet 14 that was done on Thursday. So the two problems that we're going to be working on today are both proofs by induction, and this time it's going to be applied to these recursive functions. So the first problem says that we have this function that's defined by this recursive relationship, and what makes something recursive is that a of n, this factor that we care about, is defined by the previous factor. So basically all I need to know to figure out what a of n is what a of n minus 1 is. If I know the previous factor, then I can figure out the next factor, and so on and so on. And that's kind of how induction works. Induction is a recursive process. So here we're looking at these applications. And the only thing we need is a starting point. So we know that this first a sub 0 is equal to 0. And we need to prove that for all the following factors. So we're given a of 0. So we want to know a of 1, a of 2, a of 3, all of these factors, that they're going to follow this formula, 2 to the n minus 1. And so we're going to define this statement P of n. This is not strictly necessary in a proof by induction, but I think it's really helpful. It gives us the shorthand language that we're going to be able to use over and over again. That instead of repeating a long statement, we could just say P of n. And we're going to define P of n at the beginning. So we're going to say P of n is, or rather, I'm going to use this lasso effect. We're actually defining P of n. So let's say let P of n be the statement that for all n greater than or equal to 1, a of n is equal to 2 to the n minus 1. Let me do that part again. 2 to the n minus 1. Nice. I have no idea when it's going to come out nice and when it's not. Okay, so what are our steps in a proof by induction? The first thing that we need is a base case. Sorry, I'm getting over a cold. So our first step is the base case. And here we, this was a little bit of a controversy in class, whether the base case should be when n equals 0 or when n equals 1. And the truth is, I think n equals 1 is a bit more intuitive. And that's because we have this, n greater than or equal to 1. The reason you could use 0 is because we do have this over here, a of 0 equals 0, which means that n does take the value 0, and that it has to work for n equals 0 as well. But either way you want to do it, it'll work, and maybe I'll show you both actually. Base case. So I'll start with P of 0 is the statement that I should say that a of 0 equals 2 to the 0 minus 1, which equals 1 minus 1, which equals 0, which is true. And we know that because it's given. That's one of the two things that we're given. The two pieces of information we're given is that a sub 0 is equal to 0, and also that a sub n is equal to this function 2a of n minus 1 plus 1. Okay, so now I'm going to do the second base case. And you could do either one of these. You don't have to do both, but you do have to do one of them. P of 1 is the statement that a sub 1 equals 2 to the first power minus 1, which equals 1. And that's actually also given. I didn't write all of this down, but we're also given in the problem that a sub 1 equals 1, a sub 2 equals 3, and a sub 3 equals 7. That's all given in the problem. And it doesn't need to be given because we could use either one of these formulas to derive it. So this a sub n formula will tell us that a sub 1, I'm looking at this stuff right now, that a sub 1 would be equal to 2 times a sub 0 plus 1, and a sub 0 is 0, so 2 times 0 plus 1 is just 1, and we get that a sub 1 is equal to 1. So now I'm going to get rid of all that mess. So a lot of ways of figuring out that a sub 1 is 1. We could do the math, we could use this given, but either way we've shown the base case. And that allows us to jump into the next step, which I'll do in green, and that's our inductive hypothesis. And I'll shorthand it like the cool kids and say IH. So our inductive hypothesis will be, suppose P of n is true for some n. And that's all you need to write for an inductive hypothesis. And if you define a P of n, this is all you need to write for any inductive hypothesis, provided that you've defined P of n, which we've done right up here. Let P of n be this statement. So if you want to say it more explicitly, you could say that for some n greater than or equal to 1, a of n equals 2 to the n minus 1. And we're allowed to say this. I know I repeat myself so frequently, but it's important to understand why we're allowed to say this, why we're allowed to assume this inductive hypothesis. And it's because we have shown the base case. And truthfully, this is getting into the weeds a little bit, so you could ignore this, but we actually need to use the base case of P of 1 and not P of 0 in order to use this specific inductive hypothesis, because we are assuming that for some n greater than or equal to 1, that this is true. And we're only allowed to assume that once we've shown that it's true for one of the examples, namely P of 1. P of 0 is outside the domain of n greater than or equal to 1. So I might be losing some of you. So if you don't understand that, it's not so important. Okay, so this is our inductive hypothesis. For some n greater than or equal to 1, a of n, a sub n, is equal to this 2 to the power n minus 1. So now we'll go into our inductive step, which I'll do as IS. And let's see, for our inductive step, we want to show that P of n implies P of n plus 1. And let's understand what P of n plus 1 says. And we're going to try to use P of n to support P of n plus 1. And we're going to see how that's going to work out. So there's a lot of ways of writing an inductive step. The way I like to do it is I like to write out what P of n plus 1 is saying. And sometimes when you do that, you can more easily see how we could get there using P of n. So P of n plus 1 is the statement that a of n plus 1 is equal to 2 to the n plus 1 minus 1, which also, let's just do a little algebra, which is equal to 2 times 2 to the n minus 1. Is that all right? Yeah, I think that's right. Okay, so we have a of n plus 1 is equal to 2 times 2 to the n minus 1. And here's where I'm seeing something. I see this 2 to the n minus 1, and I recognize it from a of n. If we scroll back up to the top, we see that we have this a of n equals 2 to the n minus 1, which is kind of interesting. So we could say that this is also equal to 2 times a of n. 2 times a of n would equal 2 times 2 to the n minus 1, which equals 2 to the n plus 1 minus 2. So this is not quite the same. We're going to have to do a little bit of manipulation here. But basically what we could rewrite this as, this meaning this, we can rewrite this as 2 times 2n minus 1 plus 1. Because then we're basically taking this and we're adding 1, which gets us back to this. We're subtracting 2, we're adding 1, so altogether we're getting minus 1. And it's just another way of writing this that's going to be convenient for us, because 2 to the n minus 1 is a of n. And we want to use a of n, because that's kind of how our inductive step is going to work. I know I'm being really terrible about this, but the point is, when you do an inductive step, we want to look at p of n plus 1, but we want to find the p of n within the p of n plus 1. So we're looking for the 2 to the n minus 1 within this whole mess. So initially, I'm kind of just restarting my thought process because I think I was a little sloppy there. Initially, we get that a of n plus 1 is 2 to the n plus 1 minus 1. And our goal, find 2 to the n minus 1 within it. Because we want to use a of n. To derive a of n plus 1. So we want to find this a of n equals 2 to the n minus 1. So first thing I did was I turned this into 2 times 2 to the n minus 1. And I said, okay, this is great. We're getting closer to this 2 to the n minus 1. But we haven't quite factored it out yet. We haven't quite gotten it all by itself. So then we said, okay, well, we could make this 2 to the n minus 1 as long as we add a plus 1 at the end. And this is equal to 2 times a of n plus 1. And if we go up to the top, we have it right here. 2 times a of n plus 1. So basically what we found is that a of n plus 1 is equal to 2 times a of n plus 1. And what we're given at the beginning is that a of n equals 2 times a of n minus 1 plus 1. So we're given this template of a of n equals 2 times a of n minus 1 plus 1. So these two statements are the same. Both of them are saying that the next number is the previous number times 2 plus 1. Hopefully you could see that. We're just incrementing n by 1 on the top line. So this one has n at a greater value by 1 in both cases. So at the end of the day, we're able to derive p of n implies p of n plus 1. And then our conclusion is that by the PMI, p of n implies p of n plus 1. And I'm using like extreme shorthand, but this is basically all you need to write in your conclusion, is that by the principle of mathematical induction, we have shown that p of n implies p of n plus 1, and therefore p of n holds for all n greater than or equal to 1. That's basically all we need to say, and that's the universe that we're working within. Okay, great. Now let's jump into, I did a lot of writing there. I think the less clear my thoughts are, the more writing I do. Okay, so That was a little bit sloppy, but hopefully it was somewhat helpful. Whoa, that is thick. Okay, number 2. So number 2 says the Fibonacci numbers. Maybe some of you comp sci people know about the Fibonacci numbers. Fibonacci numbers are defined by recursion. So f of 0 equals 0. That just means the first number. The next one is 1. I think f of 2. Or we don't have f of 2. We'll have to figure out f of 2. So the next thing says f of n equals f of n minus 1 plus f of n minus 2. This is really easy to understand. It means that whatever number we're up to is the sum of the previous 2 numbers. And that actually tells you why. This is why we have to be given the first 2 numbers. Because this f of 0, if you assume that we're starting at 0, the 0th index of the Fibonacci numbers, there aren't any previous numbers to work off of. And with the first one, we only have 1 previous number to work off of. So we can't use this formula until we get to the 3rd number. Hopefully that part makes sense. And that's why we're only given the first 2 indices. So now we are asked to prove that f of 3k is even for all k in the naturals. So anytime we have f of 3k, it's going to be an even number. We could start listing them. We have 0 and 1 are the first 2. Those are given. The next one is the sum of the previous 2, so it's also 1. Then the next one is the sum of the previous 2 again. So it is 2. And then we have 3 and 5 and 8 and 13 and 21 and 34. And I think that's a good place to stop. And so if we just write down the indices, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we could see that 9, 6, and 3, those are our 3Ks, our products of 3, that all of those are even numbers. Huh, that is weird. Why does that work out? Let's see. Okay, so let's define a p of n. And again, I want to say, I'm defining it, so I'm going to say let p of n be the statement that for all k in n, you can write this in any order you want, but I'm going to say for all k in n, f of 3k is even. And I'm doing a little bit of shorthand. It's in the set of even numbers, which is a perfectly fine way of writing this. So, what will be our base case? Well, I would say that our base case should be when k is 0, because that's the smallest natural number. So let's say, I made one little error here. I should say p of k, not p of n, because we don't have an n. We're not using n here. We're going to use k. So p of k is the statement that for all k in the naturals, f of 3k is even. And what do we know about this f of 3k? It's going to follow this formula of f of n equals f of n minus 1 plus f of n minus 2. It's going to be the sum of the previous 2. That's all we know. So our base case is going to be p of 0 is the statement f of 3 times 0 is even. That is f of 0, which equals 0, and that's a given. That's given right here. F of 0 equals 0 is even, which is true. And I had a couple of you asking me is 0 an even number? Remember, even numbers are 2z for an integer. It's 2 times an integer. 0 is an integer. 2 times 0 equals 0. Therefore, 0 is even. Cool. 2z plus 1 is odd. You can't write 0 as 2z plus 1. It's not possible. Okay, so our base case is p of 0 is the statement f of 3 times 0 is even. F of 0 is 0. That's given. Easy enough. Inductive hypothesis. Suppose p of k is true for some k. I could say in the naturals. It's a generalization of the base case. We've just shown that the base case is true. That was true for some k in n, namely the first k in n, namely 0. Now we're generalizing. And I'm not going to rewrite it. I'm just going to say, suppose p of k is true for some k in n. We know what that means. That means that f of 3k is even for some k. If we plug in maybe the number 3 for k, that'll be f of 9 is even. That'll be true. It should be true. Inductive step. P of k implies p of k plus 1. So how are we going to do this exactly? The p of k plus 1, let's write out what p of k plus 1 is. P of k plus 1 says f of 3 times k plus 1. It's important to remember k plus 1 is going in parentheses. We're multiplying 3 by all of it. Wherever you see a k, you're replacing it with k plus 1. So if k is multiplied by 3, now k plus 1 is multiplied by 3. So when you write this all out, it's not going to be, it's not f of 3k plus 1. That's not what it's saying. It's saying f of 3k plus 3. That's a pretty common mistake that people make when they're doing an inductive step, is that they forget to fully replace k with k plus 1. So don't be that guy. Don't be that girl. Okay, so p of k plus 1 says that f of 3k plus 3 is even. Okay, so let's write more about this. What do we know about f of 3k plus 3? Well, we know from the inductive hypothesis. Not from the inductive hypothesis. We know from what's given. This thing over here. That f of 3k plus 3 is going to be the sum of the previous two guys in our Fibonacci order. So we know that f of 3k plus 3 is equal to f of 3k plus 2 plus f of 3k plus 1. Now, remember, when we're doing an inductive step, we want to use f of 3k. We want to use our inductive hypothesis. Yeah. Our statement p of k tells us about f of 3k. So we want to use that. That's our inductive hypothesis is telling us about that. We want to use that in our proof. So what can we say about this? Well, f of 3k plus 2, f of 3k plus 1. I don't know so much about these things. They're just as unfamiliar to me as f of 3k plus 3. So let's rewrite this again. What do we know about f of 3k plus 2? It's also the sum of the previous two. We could say that for every factor, that f of 3k plus 1 is the sum of the previous two. So let's rewrite f of 3k plus 2. Let's say that's equal to f of 3k plus 1 plus f of 3k. And now we have to bring down this guy, plus f of 3k plus 1. And now we could rewrite this as 2 times f of 3k plus 1. We now have 2 of the same guy. So we'll just multiply it by 2 and simplify this. F of 3k. And now we could say we know from the inductive hypothesis that f of 3k is even. We could assume that it's even from the inductive hypothesis. And we know that 2 times anything is even. We know that f of 3k plus 1 is some integer. It's some natural number. So we could say that 2 times that is definitely going to be even. So we can now say that f of 3k plus 3 is even. And we have used the fact that f of 3k is even from our inductive hypothesis, our p of k, to prove that f of 3k plus 3 is even. That's exactly what we're supposed to do. So that's basically all we need to do, actually. And now we could say, now Professor Carbone, I'm looking at her proof right now, and she writes it nicer than I just said it. So I recommend you look at her proof. She defines some variables and shows very explicitly that this is even. So I do recommend that you look at her proof. And yeah, I'm trying to walk through the thought process of this, but yeah, I like the way she wrote it a lot. So anyway, we've shown that p of k implies p of k plus 1. That is, we've shown that if f of 3k is even, then f of 3k plus 3 is also even. That's what we've just shown. And our conclusion is that by the PMI, by the principle of mathematical induction, we've proved that f of 3k is even for all k in n, which is what we set out to prove at the beginning. Where is it? Here. Prove that f of 3k is even for all k in n. And we've done it. All right. Hopefully this was helpful. I know we have a test later this week, so good luck in your studies, and please reach out with any questions on homeworks or on Worksheet.